Hello, grade 11s. In the last lesson, I introduced intermolecular forces. So if you remember, intermolecular forces is the force between molecules holding them together either in a liquid or a solid. Now, the first intermolecular force we had a look at was called a London force. Now, if you remember, London's forces exist between all particles, but it is the only particle that exists between non-polar molecules. So here we have the example of carbon dioxide. And if you remember, when we discussed the polar covalent bond, the bond between the carbon and the oxygen, because of the difference in electronegativity, is a polar covalent bond. But because of the structure, this linear structure, the carbon dioxide overall is a non-polar molecule. And so between this carbon dioxide non-polar molecule and the other non-polar molecule, we have a weak London's force. And remember that London forces are the only intermolecular forces between non-polar molecules. London forces are weak. And so if London forces are weak, then we only have to supply a little bit of energy to overcome them. So substances with London forces have low boiling points. A London force is an example of a van der Waals force. Now, van der Waals was a scientist who researched intermolecular forces, and van der Waals forces cover London forces and the next type of intermolecular forces we're going to have a look at. The next type of intermolecular force we're going to have a look at is called a dipole-dipole force. A dipole-dipole force is also another example of a van der Waals force. So now if we recap what we mean by dipole, if you remember from bonding, it means a polar molecule. And whenever you get a polar molecule, there's an unequal sharing of electrons. Plus, if we look at the shape, it gives us an asymmetrical distribution of charge. And then that polar molecule is called a dipole. So if we look at HCl, H has an electronegativity of 2.1, chlorine has an electronegativity of 3. So there's an unequal sharing of electrons. The electrons are closer to the chlorine. So the chlorine becomes slightly negative and the hydrogen becomes slightly positive. And because of its linear structure, there's an asymmetrical distribution of charge. So this is a polar molecule. Now, if we look at the very next HCl, it is also a polar molecule, and it has a slightly negative and a slightly positive side. Now, the attraction between the slightly negative side of the one molecule and the slightly positive side of the other molecule is called a dipole-dipole force. If we have a look at SCl2, now this is an angular molecule, and the reason it's angular and not linear like the carbon dioxide is that the sulfur has lone pairs, and those lone pairs are repelling the shared pair of electrons in the bond, and so it forms an angular molecule just like water. Now, chlorine has a higher electronegativity, so there is an unequal sharing of electrons, and the electrons are closer to the chlorine. So the chlorine becomes slightly negative and the sulfur becomes slightly positive. So if we look at the angular structure, there's a concentration of electrons over here by the chlorines, and there's less electrons up here by the sulfur. And so that means there's an asymmetrical distribution of charge, and so this entire molecule is a polar molecule, which means it's a dipole. So if we look at the very next molecule, the attraction between the slightly negative chlorine over here and the slightly positive sulfur in the next molecule is called a dipole-dipole force. As I said, dipole-dipole is also a type of van der Waals force. Now, between polar molecules, there's the dipole-dipole force, plus there's the London force, because London forces exist between all particles. Now, the intermolecular force between dipoles or polar molecules is London forces and dipole-dipole forces. The dipole-dipole intermolecular force is stronger than a London's force, so the boiling point is higher. Because the dipole-dipole force is stronger, that means we have to supply more energy in terms of heat to break those London forces and the dipole-dipole forces, and that means we have a higher boiling point. So if we have a look at an example where they give us two substances and two boiling points, and they ask us to explain the difference in boiling point. For example, CO2 has a boiling point of minus 78.46 degrees Celsius, and SCl2 has a boiling point of 59.6 degrees Celsius, and they ask us to explain the difference in boiling point. Now, I would like to suggest that you use the following steps, or think about the following steps when answering the question. So first of all, you must identify each substance's intermolecular forces. So in other words, I must identify the intermolecular force with CO2 and the intermolecular forces with SCl2. Then number two, you compare the strength of the intermolecular forces. Then you identify which will need more energy to overcome. In other words, the stronger one will need more energy. And then you make reference to the boiling point. So let's do that with this example. So first of all, identify each substance's intermolecular force or forces. Now remember, everything has London forces. So carbon dioxide we know is a non-polar molecule. So it would be between a non-polar molecule and another non-polar molecule of CO2, and so that would be a London force. Now SCl2 is a dipole, and so as I explained in the previous slide, it would be a dipole-dipole and it would have London forces. So step one. Carbon dioxide is a non-polar molecule, so there are London forces between the molecules. SCl2 is a polar molecule, which is called a dipole, so there are both London forces, because London forces exist with everything, and dipole-dipole forces between the molecules. Then compare the strength of the intermolecular forces. Dipole-dipole intermolecular forces are stronger than London forces. So now SCl2 has dipole-dipole and London forces, and CO2 only has London forces, and the dipole-dipole forces are much stronger. So we say dipole-dipole forces require more energy to break. That's because they're stronger. Make reference to the boiling point. SCl2 therefore has a higher boiling point than CO2. Sometimes they give us some substances that have exactly the same type of intermolecular forces, and so we need to distinguish between the strength. Now, if you refer back to the slideshow on London forces, I told you if we have a look at the molar mass, an increase in molar mass influences the strength of the intermolecular force. The higher the molar mass, the stronger the intermolecular force. I also said surface area has an influence on the strength of the intermolecular force. So if we look at HCl and HI, both of them are polar molecules. So there is a difference in electronegativity between the H and Cl. There's a slightly positive side, a slightly negative side, so it's a dipole. The very next molecule is also a dipole, so there's an electrostatic attraction between the dipoles. So here we're going to have dipole-dipole forces and London forces, and remember both of those are a type of von Neumann force. If we look at HI, there is a slight difference in electronegativity, so again there's going to be a slightly negative side and a slightly positive side, and the electrostatic attraction between the two molecules is going to be dipole-dipole and London forces again. So here we have exactly the same type of intermolecular forces. So now we have to look at something else, and in this case we look at the molecular mass. So the molecular mass of HCl is 36.5 grams per mole, whereas HI is a bigger molecule. It's 128 grams per mole. And if you remember from slide 1, I told you that if you have an increased molecular mass, you have an increased electron cloud density, and that's what makes the intermolecular force stronger. So if we were to explain the difference over here in the boiling point, you can see HI is at minus 35 and HCl is minus 85. So HI has a higher boiling point than HCl. Remember, these are negative numbers. So if we go through the same steps as before, we have to first identify the type of intermolecular force. So HCl is a polar molecule, so there are London forces and dipole-dipole forces between the molecules. HI is a polar molecule, a dipole, so there are both London forces and dipole-dipole forces between the molecules. So now we see we are dealing with exactly the same type of intermolecular forces. So now we're going to use the molar mass to distinguish between the boiling points. So we say HI has a larger molecular mass than HCl, therefore an increased electron cloud density, which means stronger intermolecular forces. There are more electrons involved. The stronger intermolecular forces require more energy to break. HI, therefore, has a higher boiling point than HCl.